Okay, so moving forward, when we look at this problem, you maybe want to hear me, let's say, read this out, and then you might want to hit pause should you be tuning in a little later. But what it says is a 2.5 gram sample of copper 2 sulfate has an unknown amount of water in it called a hydrate. So after heating, there was approximately 1.59 grams remaining in a crucible. So what is the formula of the hydrate? Although this is not a crucible, it's called an evaporating dish, but the concept is still the same, where with a crucible you set it on top of a clay triangle over a Bunsen burner. So what you're doing is you're heating that substance and you're driving off water. So for example, or for instance, we've got what we see is ferric chloride, or excuse me, ferric sulfate, which would mean nothing to you because there's ferrous sulfate and then there's ferric. Why might you have two different names for this compound? You don't need to know it, but well, in this case, yes, it would be the same thing. For copper, you'd have cuprous and cupric. This is ferrous and ferric. So you have two different types of ions that you could find in this formula, okay? Whether it's iron 2 or iron 3. That's how we name things, just like you see copper 1 or copper 2. It used to be, probably years ago, before a lot of this nomenclature had changed, would be you would have cupric sulfate, okay? Rather than cuprous, which would be copper 1 sulfate, okay? Maybe we just made things too easy for people. I don't know, could be. But before I forget, I do need to take roll, so I'm gonna hit pause, and then you, like I said, after hearing me explain this, you can write this down if you so choose. So we walked around and said, what is written right in front of this H2O? And you all had said it is a variable called X. Well, variable can mean anything.
Is it X or is it 10?
It's X, because if it was 10, it would be written like that. Okay? So what we mean here is, just like you would have seen on that bottle, so we know that this is in the substance. Okay? And then you could say X or dot. Okay, what this means is there 2 moles of water? Is there 3 moles of water? Is there 4? Is there 5? It could be 9. It could be any one of these numbers, which means that's how many moles of water are locked up in this compound. Because how do we know this? Well, one, we're telling you. What does that mean to you? Hydrate. Well, it does mean hydrogen and oxygen. That's true. It means water, because if you hydrate something, you, or even yourself, you're adding water to it. Okay? So within this compound that we're looking at, we know that this is in there, but how many moles of water are locked up in this compound? That's something that you can experimentally determine. Like in this case, you don't know what's in this bottle other than iron 2 sulfate. Okay? No. Iron 3 sulfate. But you don't know how many moles of water are in there. The reason I picked this one is because it actually had the unknown on there written like this. So in this example, it's going to be one of these numbers that you see here. Might be 2 moles of water, might be 3, might be 4, 5, 9, maybe 7. I just thought, well, we're increasing by increments of 1. Maybe we should just go ahead and jump up by an increment of 4. So that's what we decided to do. So then, in this example, you have 2.5 grams of copper 2 sulfate in here. And then what happens is you are heating it up and you're driving that water off. Okay?
So you're evaporating the water.
Yeah, I suppose you could say you're evaporating it. That's true. So how we determine that is as follows. We started with this, okay? We heated it up after a certain amount of time, this hydrate that has all of these components in here. Again, we don't know which one, okay? And then after this, there's about 1.59 grams remaining in the crucible. So our main idea is, why would these two numbers be different? We must be removing something from within this crucible. It's something that you just said. Yes, you're heating the water up and it is evaporating out of here. Or you're boiling it out, whichever way you want to look at it. So you are removing the water in this hydrate after you heated it up. Of course, you might say, well, how do we even know that? We just have two numbers here. It has nothing to do with water. Well, yes, it does. And the reason for that is because it's something you have not learned yet. Okay? So what this means is, if we had 2.5 grams to start with, then after this certain amount of time, we recorded 1.59, something must have been removed from this, and that would be water. Okay? So then to determine that, okay, and if time allows us to, the activity that we do is a lot more elaborate than this, because this problem here is already taking into account what the mass of the crucible is and everything else within that nature. But in this case, okay, when we subtract these two, okay, we have 2.5 minus 1.59, okay, and that is, okay, we got papers piling up here. Oh, that's your evaluation. Okay. So then we get 0.91, which, again, when we look at this, we might say, well, this doesn't mean anything to me. Well, so let's look at this. This has the copper 2 sulfate in it. Is this formula written correctly like this?
Sure.
Do we need to change anything?
It's right, because sulfate has a -2 and copper.
Okay. So this has a -2 charge. This has a +2 charge, so that adds up to 0. So this 2.5 grams has this copper sulfate in it and water, or H2O. So then what had happened after a few moments, 5 minutes, 10 minutes, I really don't know. Because what you do is you would continually heat this until that number just does not change anymore. Because you've already driven?
Finish it and then.
Okay, so you removed, there we go. So you remove the water because this is still a solid here. So this is what we call an anhydride. Okay, so if this is the hydrate, the powder that you would see remaining is what we call an anhydride. So how much water was in there? Well, we take the amount of the anhydride and subtract that from our total, and then that gives you how much, what do you think? Grams remaining of what though?
Grams of copper.
Well, it's going to be one or the other.
Wait, no, it would be copper and sulfur.
So then this is how much water we drove off. Okay? So this anhydride is the type of powder that you would see. So you removed, okay, 0.91 grams of water. Now you're going to be in what we call a little more familiar territory. Yes?
Since you boil out the water and there's oxygen in water, would that also take out part of the oxygen?
Part of this here?
Yeah.
No. Because this sulfur, okay, and this copper here are going to be holding on to those electrons and the oxygen is just not going to let it go. So how do we know this? This is maybe one of the, and we've done a little bit of this before. Okay, we know this whole thing is a -2. Yes, that's correct, which must mean we see that these two elements are in the same column. Oxygen has what for a charge? Negative what? -2, and how many of them do you have? So that must mean the oxygens alone are -8. And you might be telling yourself, now, wait a minute here. I thought you told us that the charge of sulfate is -2. Well, yes it is. We've only talked about the oxygen. So that must mean that even though sulfur is in the same column, this has to have a positive charge, which it does. So if this has a charge of +6, okay, and you add a -8 to +6, what do we get? -2. And that is the overall charge of that sulfate. So you have to take into account you have these copper ions at +2, these sulfur ions at +6. That is holding on to those oxygen atoms. And I could see where you could think, well, does that take some of the oxygen out? No, because the electrons are probably held together in this compound. It just does not release that in all of this anhydride now. So then, excuse me, if this is the copper 2 sulfate and the water, and then this is the water, what's the only thing left from what we started with? So this is your copper 2 sulfate. Okay? So now, like I said, we're into maybe a little more familiar territory because we've got grams that we can utilize, and then we've also got grams of, I suppose I can just write it here, that we can utilize as well. So now that we see that there is a number measured in grams, we're probably going to change that to what would you guess or think? Right, you're going to change that to moles now. Okay? So then we've got 1.59 grams of copper 2 sulfate. That's not what I wanted. Of copper 2 sulfate. Then you correctly said we're going to change that to moles. Okay? So then when we look at this, let's see here, oxygens 64, and this is just a rough estimate. Sulfur is somewhere around 32, and then copper is 63. So 6 and 9, and then we've got 9. We got 159, and we're supposed to come up with, yes. So 159.6 is what the author says. Okay, so that 159, that's the atomic mass of this. Where does that go here?
The bottom.
Okay, so 159.60 grams of copper sulfate gives you one what? That's going to give you 1 mole of copper sulfate. Okay? So we would calculate that out, and it's going to give us a number in moles. So that's just your anhydride. We still have the water to do yet. So we're going to start with 0.91 grams of H2O. Convert that to moles now by dividing by what?
Where did you pull that number?
Atomic mass of 17.01.
Which one?
Oh, okay, never mind.
Okay.
2 I meant.
So then what is it that we would put here in this next step? We have a number to put on top. We have to put a number on the bottom, but which one is which?
Grams on the bottom.
Okay, grams of
H2O.
H2O is on the bottom.
Which is 18.02.
Mole of water on top. Okay, then 18.02.
18 or 18?
18, oxygen
17.
16, and then hydrogen is
Where do you get 17 from?
16 plus 1. Yeah,
But there's H2O.
There's two of them though.
16, what's the bottom number?
Eight.
I'm sped.
What? Oh. So then that gives us a number. We divide this out, okay? Does that give you like 0.1 just by looking at,
Yeah, I'm sure. Yeah, probably.
okay? So 1.59 divided by 159.6 gives you, oh geez, I was way off. Okay. 0.00 996. So we're going to go, I would suggest that you do 3 non-zero digits. Now, should this come out to 0.00990, that's fine. But if you can have, when you start with your significant figures here, do 3 non-zero digits. Does that make sense?
Yeah.
We look at it that way. Then when we do the water, okay, 0.91 divided by 18.02, that gives you 0.05, okay? And then we're going to do 0.4, okay? And then, because there's a 0 in here, I think we can just utilize that number. I think would be just fine. Okay?
Can you times the smallest number by the?
No, that's you're close. Okay? Because when we do this, with every time you figure out a hydrate, you would say this magical number that's measured in moles. Okay? We're going to say moles is going to equal the moles of water. We'll just put mole water divided by moles of, is it hydrate or anhydride? Anhydride. Because if we do hydrate, then we're going back to how we started. So then this is moles of anhydride.
What is the am from?
It just means without water. Okay.
So it's like non.
Well, when we look at it this way, maybe how do farmers replenish their nitrogen in the soil in the spring? Well, soybeans is only going to put you so far. Yeah, and that fertilizer is ammonia. And not only is it ammonia, it's called anhydrous ammonia because there's no water in there. So that's what we mean by this. So now our moles of X, okay, whichever one of these is what we had calculated this from. So our number of moles equals, okay, so this is the moles of water, so that goes on top, 0.0504. Then our moles of our anhydride, 0.00996. And let's see once what we get when we divide those two out. 0.0504 divided by 0.00966.
Or could you do like times 10 to the third?
Don't make it complicated. Say what?
Okay, what he's saying back there is 5.04 times 10 to the negative second, 9.66 times 10 to the negative third. Yes, you could do that. I punched it in my calculator wrong because I came up with 5 1/4, and I don't think that's right. 0.0504 divided by 0.00966.
It's 996.
What did I say?
966.
966? 996. Okay. You are correct. It should be, and shoot, all I had to do was look over here. 996. let's hope. Because otherwise I came up with 5.21. That's not right either. Okay, so 0.0504 divided by 0.00996. That comes up with 5.06, which I think we can just say 5. So of all of these, that's what you would have on your bottle. Because remember, when we were walking around, everyone looked at this formula, and it just had ferrous sulfate, or the formula for iron 3 sulfate, and then it had the letter X after it. So that must mean that in this compound, if this was copper 2 sulfate, it would say CuSO4, and after the X, or you could put dot 5, because there's 5 moles of water in here. I don't know if you could say that it's a ratio of moles to copper 2 sulfate, but that's just one of the things that you would experimentally do to see what maybe an unknown substance is. Because if you leave this set out on the counter, okay, what's going to happen is within this crystals, you're going to see little puddles of water underneath it, because there's water locked into that compound, just like what you would see here. This one's really notorious, I think, that leaves lots and lots of water underneath it.
Immediately reacted when it touches water? Are there any?
Okay, repeat that again.
Like, what happened? Is there any chemical that'll like have a reaction?
Well, it doesn't even need to be a chemical. It can just be an element. You can just take anything out of the alkali earth or alkaline series. Those are the alkaline metals, which is what column from physical science?
Number 2?
Those are alkaline earth. You're close.
Number 1.
Yes, the alkali metals is column 1. So is lithium in column 1?
Yep.
So any battery you look at, that's why they call them lithium-ion batteries. Okay, those are the alkali batteries, because it's from the metal lithium in column 1.
Isn't salt sodium?
And nope, then it would be sodium oxide. Yeah. Sodium chloride is salt. Potassium chloride is salt. And oddly enough, what you can do, I think, is I remember this vaguely on the farm that I worked at when I was your age in school, because when the baseball season rolled around, well, that was in the summertime. Same with golf. So I did. So, but what I remember is working on the neighbor's farm during the winter time. Okay, what is it that a farmer could do to really have a lot of weight on the back end of the? Yeah, you can put something on your 3-point hitch. You can do that, but you can do something with your tire. Okay, now careful. You can put water in there, but it would freeze unless you add something to it. And for some reason, what stands out in my mind is I think a solution of calcium chloride gets placed into there. Okay? So what happens then is, I'm going to hit pause for just a moment. But, well, and you wouldn't necessarily say ice melt. You would just say salt. Because it's either.
Said that to anyone?
Have I? No. Because are people really going to listen, or are they going to say, what does he know? Well, it could be. Maybe say that too. Okay. So, but what comes to mind is in the wintertime, if you want to add weight to the back end, you would put a liquid in there. And it's a liquid solution of, I think, calcium chloride. So that water will not freeze because you have some of that salt in there. And what did we say that salt does with the freezing point of water.
Drops temperature.
It lowers it. Depending upon what the concentration is, I would be led to believe that it probably could lower it down to maybe even below zero, because, and I'm not sure of the specifics of it, but I think that as long as you store it inside, even if it gets really, really cold, then even if it gets down to zero, which we could say 0 degrees Fahrenheit, the moment that you start moving that fluid, it's just, you can just hear it jostling around in there. So as long as you have that moving, what I'm trying to say is it's not going to freeze to a solid. Okay, not that it's sort of linked to this, but not exactly, because again, you are lowering the freezing point. That's why what would happen if you did not put that salt in ice cream? It would just remain soupy. Okay, if I'm interpreting that right, or it gets to be rock hard, don't it?
What?
When you put salt in that ice cream.
Salt in your ice cream.
Homemade ice cream.
Homemade, yes.
Put it in ice.
But don't you put a little bit of salt in? Yeah, so you're nodding your head, yes, I think there's something to that. Yes. Now whether I got that correct, I don't know. Okay. So hydrates, we'll be talking a little bit more about this tomorrow, since it didn't get erased by someone's hair, so we'll we weren't paying attention, that's okay. I said, it still says hydrates over there, even though someone didn't erase it with their hair. So, and that's okay. I mean, we'll talk more about this tomorrow, so we'll catch up to you next time.